Поехали. Окей. Значит, сначала по-русски представлю. Сегодня у нас выступает Татьяна Викторовна Шульман из Гетеборга. Uh, Today our speaker is Tatiana Shulman from Gothenburg University, and the title of her talk is Central Sequence Algebras via Nilpotent Elements. Please.
Thank you very much, Losha, and thank you very much for inviting me here. I'm always happy to give a talk here. Um, I made full screen, so I see you, but I don't see chat. So if you want to ask something, just interrupt any moment, okay?
Okay.
Um, I'm going to talk about my joint work with Dominic Enders. The work is about central sequence algebras. So I will start with the definition of a central sequence. We have a sister algebra A and a bounded sequence xn of elements of this algebra. We say that it's central if it approximately commutes with every element of the algebra. Central sequences can be considered in the C-star setting, and in this case, convergence is understood with respect to the operator norm, but also they can be considered in for von Neumann algebras, and then by norm we mean the tracial norm. If one tries to come up with an example of a central sequence, then the first thing that comes to head is just to take a sequence of central elements, those which actually commute with everything, and add a sequence which converges to zero. Of course, we would get a central sequence. Such are not very interesting and are called trivial. And the whole point is whether there are non-trivial ones and how to find them. Also, in the definition of a central sequence, we can replace usual convergence by convergence along ultrafilter. For sister algebras, it doesn't really matter. But for Neumann algebras, it's very convenient. They always consider convergence with respect to ultrafilter. Central sequences can be organized in a sister algebra in the following way. For that, let's consider product of infinitely many copies of A. By this I mean that we consider sequences with coordinates inside our sister algebra, and we consider only bounded sequences. Then it's a sister algebra with the coordinate-wise multiplication and addition. And this supremum gives a sister norm on this algebra. Inside this algebra, there is an ideal of those sequences which converge to zero. And again, if we deal with sister algebras, then we consider convergence in operator norm. And if we deal with von Neumann algebras, then it's with respect to tracial norm. Either way, it's a closed ideal, closed in operator norm. So if we take quotient by this ideal, we get a sister algebra. It's called an ultra power of the original sister algebra A. And let's denote by pi the canonical surjection, which sends every sequence to its class of equivalence. Now, the original sister algebra embeds into its ultra power via constant sequences. So A sits inside its ultra power. Therefore, we can consider its commutant inside the ultra power. And that's what's called the central sequence algebra. At least for unital sister algebra, the central sequence algebra is defined as its commutant inside the ultra power. And why it's called like that? It's because if we take an element of this sister algebra, any its representative is a central sequence. Or very simply speaking, what we just did, in fact, we took all central sequences and considered them modular sequences converging to zero. What we got is this central sequence algebra. For that's how it's defined for unital sister algebra A. For non-unital, this object that we got would be too big. By the way, can you see the upper line of on my slides?
Yes, we
Yes,
do.
okay,
Mhm.
great. So in non-unital case, why it's too big? Because, for example, there will be too many non-interesting sequences here. For instance, every non-unital sister algebra has an approximate unit, and it has lots of them. So let's consider a difference between two approximate units. Then, of course, it's central sequence because it approximately annihilates every element, and therefore it approximately commutes with everything. And such sequences are not very interesting, so one wants to get rid of them. By this reason, one considers the annihilator of A inside its ultra power. So it's images of those sequences which approximately annihilate every element. And then one additionally takes quotient by this annihilator. That's how it's defined for a non-unital sister algebra. In unital case, this annihilator will be just zero. So we get the original definition. Historically, central sequence algebras at first appeared in the von Neumann algebras theory. It was in 60s. At that time, people knew only finitely many to-one factors which they knew were non-isomorphic to each other. I heard that they knew 9 non-pairwise isomorphic to-one factors. And already to construct those finitely many, they needed to use central sequence algebras. And then Duza Magdaf constructed at first countably many and then uncountably many pairwise non-isomorphic to-one factors. And central sequence algebras were her main tool. And while people were so since then, since central sequence algebras are a crucial thing in von Neumann theory, and while people were working with central sequence algebras, they realized that there are two properties which are in particular important to look at. Namely, it's important to look when the central sequence algebra is trivial, meaning that all central sequences are trivial. And it happens exactly when a to-one factor doesn't have the so-called property gamma. And the second property, which is important to look at, is when the central sequence algebra is abelian. And Magdaf proved that it happens exactly when a to-one factor is not isomorphic to itself tensored with the hyperfinite to-one factor. And those which are isomorphic to itself tensored with the hyperfinite one are called since then Magdaf factors. So after all those successes in von Neumann algebras theory, people wanted to use central sequences, tried to use them to study separable sister algebras. And in particular, they considered the same two questions: when the central sequence algebra is trivial and when it's abelian. And they proved that. So the first question was answered by Ackermann and Pedersen, and they proved that the central sequence algebra is trivial exactly when A is a continuous trace sister algebra. I will not tell now what is a continuous trace sister algebra because it's not so important for the talk. I only want to say that um, it's a very narrow class of sister algebras. And that's a huge difference with von Neumann case because lots of interesting to-one factors do not have property gamma, but not so many sister algebras have continuous trace. The second question wasn't resolved, but there were partial results. In particular, John Phillips made a huge progress here. So what he proved? He proved that in unital case, if a sister algebra is either simple or contains compact operators, meaning that or it's a sister algebra of operators on a Hilbert space containing all compact operators, then the central sequence algebra is not abelian. That was in 80s, and 20 years later, central sequence algebras appear again, this time in the context of the classification program for simple nuclear sister algebras. It started with the work of Kirchberg. He found a remarkable connection between properties of a sister algebra and properties of its central sequence algebra. Since then, one considers a central sequence algebra as sort of invariant of the original algebra, which contains lots of information about the original sister algebra. Just to say you a few examples. He had lots of results, but I will say you a couple. And if you don't know all those words, it doesn't matter because it's not important for the rest of the talk. For instance, he proved that a separable nuclear sister algebra is simple and purely infinite if and only if its central sequence algebra is simple and not equal to the complex numbers. Also, he proved that a unital separable Z absorbing. So what's Z here? Z is the Zhang-Su sister algebra. It's a really important object in classification. It plays the same role as the hyperfinite factor plays for Neumann algebras. In particular, main classification results, they are in two groups. They are either for purely infinite sister algebras or for Z-absorbing algebras. And Kirchberg proved that both classes are very much described by their central sequence algebras. And since this work, central sequence algebras is a crucial tool in classification. In particular, that question of when central sequence algebra is abelian was considered again, and Ando and Kirchberg proved that if a sister algebra is not type 1, then its central sequence algebra is not abelian. What is type 1, I will say a little bit later. Ozawa gave an alternative proof, but only in the unital case. In fact, Ozawa's proof went along the same lines as John Phillips' proof. They both used Kahn's technique, which connects central sequence algebras with automorphism groups. And Ando and Kirchberg also use for Neumann algebras, but in a very different way. Okay, so from now on, I will focus on this question. When is a central sequence algebra abelian? In principle, it would be interesting to know more things. For instance, when it's n subhomogeneous. N subhomogeneous means that all irreducible representations have dimension not larger than n. For instance, one subhomogeneous it's exactly abelian ones. And Ando and Kirchberg's proof shows that if a sister algebra A is not type 1, then its central sequence algebra is not only not abelian, but even not subhomogeneous. So it means for not type 1 case, everything is clear. So we now can restrict our attention to type 1 sister algebras. And in this case, Ando and Kirchberg say that they don't have an idea how to characterize when central sequence algebras of type 1 algebras are abelian, but they construct examples showing that in this case everything is possible. Sometimes type 1 algebras have abelian central sequence algebra, sometimes not abelian. Now it's time to say what is a type 1 algebra. A sister algebra is called type 1, or also called GCR, if for every its irreducible representation, its image contains all compact operators. For instance, a very familiar sister algebra, which is type 1, is the Toeplitz algebra. Now, one more class of sister algebras called CCR. It's a mono class. It consists of those sister algebras for which image of every irreducible representation consists of compact operators. As an example, we can consider the sister algebra of all continuous matrix valued functions on some space, for instance. It's CCR. And Toeplitz algebra is type 1, but it's not CCR. It's not CCR because Toeplitz algebra, it's by definition the sister algebra generated by unilateral shift. So it's by definition, it's already represented by operators, and it's irreducible representation. It contains all compact operators, but not only them. So it's not CCR. We are going to consider type 1 sister algebras, but we will have to separately consider two cases. The first case is when A is type 1 but not CCR. And the second case will be when A is CCR. So now A is type 1 but not CCR. In this case, we are going to prove that the central sequence algebra is never subhomogeneous. And it's not hard to prove that to do this case, it's sufficient to consider the case when A is represented by operators in a Hilbert space and contains compact operators. It's sufficient only in this case to show that the central sequence algebra is not subhomogeneous. So now let me tell you a little bit about our strategy. So a technique that we use. Oh, no, before that. So we consider this case. A contains compact operators. But if you remember, John Phillips already considered this case. And he proved if such sister algebra is unital, then the central sequence algebra is not abelian. But the problem is that his proof works only in the unital case, and his proof does not say anything about subhomogeneity. So to address non-unital case and show non-subhomogeneity, one needs some completely different technique. And our technique, all our techniques, will be based on the use of nilpotent elements. So let me leave for a while central sequence algebras and talk a little bit about nilpotents. What is a nilpotent of order n? Everybody knows. In sister algebras, nilpotents have a wonderful property. They are liftable. It was discovered in a very deep work of Olsen and Pedersen. So what it means, liftable? It means that if we have a nilpotent element of order n in some quotient sister algebra, then we always can lift it to a nilpotent of the same order, meaning that we can always find its pre-image in the sister algebra A, which is also a nilpotent of the same order. And moreover, it's possible to do it preserving the norm. So a nilpotent contraction lifts the nilpotent contraction. And the consequence of the latter result is stability of nilpotent contractions under small perturbations. So simply speaking, if we have an almost nilpotent contraction, then it has to be close to an actual nilpotent contraction. More precisely, given epsilon, there is a delta such that as soon as we have in some sister algebra an element whose nth degree has norm smaller than delta, then at the epsilon distance from this element, there must be a nilpotent contraction. So the relation of being a nilpotent contraction is stable under small perturbations. We will use it. What's good about nilpotents is that they can be used to characterize classes of sister algebras. For instance, there is such a folklore result, which says that a sister algebra is commutative if and only if it doesn't contain any non-trivial nilpotent elements. And there is a generalization by Hedwin, which says that a sister algebra is n subhomogeneous if and only if each nilpotent element in A has order not larger than n. And as it often happens, one of directions here is easy and one is hard. So the easy direction is that if a sister algebra is subhomogeneous, then each nilpotent has order not more than n. Because image of which irreducible representation will be consisting of matrices of size not larger than n. Among such matrices, there is no nilpotent of order larger than n. And since it's true for every reducible representation, it's not hard to understand that it's true also in the sister algebra. So this direction is easy. But the other one, that suppose each nilpotent has order not larger than n. Why is then every reducible representation is n-dimensional or smaller than n-dimensional? This is not obvious. In fact, to prove that, one needs to use liftability of nilpotents. Furthermore, nilpotents can characterize a bigger class. There is a result by Victor Shulman and Yuri Turovsky, which says that if A is a type 1 sister algebra, then the spectral radius function is continuous on A. In principle, a spectral radius function is only a semi-continuous function. But if A is a type 1, then it turns out that spectral radius function is continuous. And this implies that the closure of nilpotents in the sister algebra must consist of quasi-nilpotents. A quasi-nilpotent is an element whose spectral radius is 0. Nilpotents, of course, also have spectral radius 0. So if nilpotents converge to something, then since spectral radius is continuous, this limit also has to be quasi-nilpotent. So it's consequence of the previous statement. And it turns out that the converse implications also hold. So if a sister algebra is not type 1, then we always can find nilpotents which converge to something not quasi-nilpotent. So it means we have a characterization of the class of type 1 sister algebras in terms of nilpotents. So if algebra is not type 1, we always can find some nilpotents which converge to something not quasi-nilpotent. But in some, not all, type 1 sister algebras, the closure of nilpotents can even contain a normal element. For instance, in B of H, one can find quasi-nilpotent operators which converge to a normal operator, which is surprising fact, proved by Voiculescu originally. And one can show easily that if the closure of nilpotents in a sister algebra contains a normal element, then A cannot even be residually type 1. Residually type 1 means that it admits a separating family of homomorphisms to type 1. So in other words, if the closure of nilpotents contains a normal element, then A is really huge. That's what we can say. Now let's return to central sequences. So we stopped at this place that we want to prove that a type 1 but not CCR sister algebra cannot have a subhomogeneous central sequence algebra. And we discussed that for that it's sufficient to consider the case when A contains K of H, compact operators. So we want to show that such sister algebra has non-subhomogeneous central sequence algebra. I should say that it's not possible to do it directly because it's not known anything about irreducible representations of central sequence algebras. So one just cannot check what's the dimension. But let's instead look at nilpotents. Since subhomogeneous algebras are characterized in terms of nilpotents, let's look at nilpotent elements. Let's try to show that the central sequence algebra contains a nilpotent of any order. Then we will be done. So we want to construct a nilpotent elements in our central sequence algebras. But how can we construct them? Out of what can we make them? Or any elements of central sequence algebra? How to construct them? And the main idea, so our strategy is to consider the Kalkin algebra. Let's consider the Kalkin algebra and the canonical surjection from B of H to the Kalkin algebra. So our main strategy is to look at the commutant of a sister algebra, of image of the sister algebra in the Kalkin algebra. So we produce a construction which I will not describe here because it's technical. I only will describe what it does. So out of element of the commutant in the Kalkin algebra, we can produce an element of the central sequence algebra. And if we have a nilpotent element in the commutant, then the construction produces a nilpotent element in the central sequence algebra out of that. Moreover, if we have a convergent sequence of nilpotents in the commutant, then it gives rise to a convergent sequence of nilpotents in the central sequence algebra. And if a sequence of nilpotents in the commutant converges to something normal, then the same will hold for the convergent sequence of nilpotents in the central sequence algebra. So it means that if the commutant in the Kalkin algebra is big in the sense that it contains lots of nilpotents, then the same will be true for the central sequence algebra. And it remains to notice that the commutant in the Kalkin algebra is always big. We prove that it always contains a copy of B of H. And B of H is, of course, huge and certainly contains sequence of nilpotents converging to something normal, to a normal operator. So now we can say that the central sequence algebra of our original algebra certainly contains a convergent sequence of nilpotents converging to a normal element, which means, as we already discussed, that it cannot be even residually type 1. So that's what we got so far. That if we have a sister algebra of operators on a Hilbert space, which contains all compact operators, then its central sequence algebra cannot be even residually type 1, in particularly in particular subhomogeneous. It means, yeah, and that was enough. Well, by the way, in principle, V of H can be replaced by multiplier algebra and compact operators by an essential ideal. The same construction will work. But now we can conclude that if a sister algebra is type 1 but not CCR, then the central sequence algebra is not residually type 1 and therefore not subhomogeneous. Which means that from now on, we can restrict our attention only to CCR algebras. And that will be our second step. And to deal with this second step, I at first need to tell you about something called Phillips condition. And before that, a definition. An element of a sister algebra is called, we say that it has a global rank not larger than n if for each irreducible representation pi of a, rank of pi of a is not larger than n. So any irreducible representation sends this element to an operator of rank not larger than n. In this case, we say this element has global rank not larger than n. And a sister algebra is called a Phillips algebra, or one says it satisfies Phillips condition if it's generated by elements of global rank 1. It's not the original definition of Phillips condition. Phil defined it in much more complicated terms, but it's an equivalent reformulation. Now let's look at examples. For instance, if our sister algebra is the sister algebra of compact operators. In this case, all irreducible representations are unitary conjugations. So any rank 1 operator will have global rank 1. And rank 1 operators generate all compact operators. So certainly that this algebra has is a Phillips algebra. Now let's look at another example. Let's consider the sister algebra of all matrix-valued functions, so continuous functions on the interval 0, 1. Those functions take values inside 2 by 2 matrices. And we consider only those functions which at point 1 take scalar value. That's our sister algebra. Let's see whether it has whether it satisfies Phillips condition. Let's look at first at the reducible representations. So here we have lots of two-dimensional irreducible representations. They correspond to evaluations at points smaller than 1, and one-dimensional representation corresponding to point 1. Now let's take some function f, which at point 1 is not 0. Then at point 1 it takes scalar value not equal to 0, so it has rank 2. Rank of f of 1 is 2. But rank is a lower semi-continuous function. So at nearby points, rank f of t also should be at least 2, and at most, of course. Which means that those representations corresponding to points which are close to 1, they will send f to rank 2 operators, which means f does not have global rank 1. Conclusion. To have global rank 1, a function have to vanish at point 1. And such functions, of course, do not generate the whole algebra. So this algebra is not a Phillips algebra. So even such a small, nice sister algebra might not be a Phillips algebra. But for instance, if we consider matrix-valued functions which at point 1 take diagonal values, then everything is fine. It's a Phillips algebra. The next definition, we will say that a sister algebra A satisfies Phillips condition of order n if it's generated by elements of global rank not larger than n. For example, if we consider functions on 0, 1 with the values in 3 by 3 matrices, and say those functions at point 1 take values of the form lambda, lambda, mu, then by the same arguments as before, it will satisfy Phillips condition of order 2, but not of order 1. The next example shows that a CCR algebra, even unital one, might not satisfy Phillips condition of any order. For that, let's consider this standard UHF algebra when we embed complex numbers in M2, M2 into M4, M4 into M8, and so on. And how we embed? We embed each matrix, say, each matrix we send to, say, matrix T, we send to matrix TT. So, like, multiple each matrix twice. Such a inductive sequence has an inductive limit called m2 in the power infinity. It's a so-called UHF algebra. And now we will consider a telescope associated with this inductive limit. What is a telescope construction? So a telescope consists of functions, continuous functions, on half of line with values inside the inductive limit. And we assume that at infinity functions have a limit inside this inductive limit sister algebra. And we consider functions, in our case, functions which at the interval from 0, 1 take value inside M2. At interval from 1 to 2, they take values inside M4, and so on. It's called a telescope associated with given UHF algebra. This is not a CCR algebra. It has lots of irreducible representations which do not contain compact operators. So it's not even type 1 algebra. But we will consider a subalgebra of it, which consists of those functions which at infinity take scalar values. This is already a CCR algebra. All its irreducible representations correspond to evaluations at points. So all irreducible representations finite dimensional. And we can prove that, in fact, it doesn't satisfy Phillips condition of any order. So why I am talking about Phillips condition? It's of course because we are going to prove that for a CCR sister algebra, its central sequence algebra is n subhomogeneous exactly when A satisfies Phillips condition of order n. There are two directions here, and each one requires its own technique. The only thing in common between those techniques is that both use liftability of nilpotents. So the if direction, so the direction, suppose that f of A is n subhomogeneous, then A satisfies Phillips condition of order n. This one is requires the most efforts, and it's really not possible to describe it, the strategy shortly. It's really technical. So this implication I will skip. But the other one, suppose A satisfies Phillips condition of order n. Why is then f of A n subhomogeneous? This implication, a strategy for that, I can describe very shortly, so I'm going to do this now. So we have a sister algebra which satisfies Phillips condition of order n, we want to show that its central sequence is n subhomogeneous. But first we will need a very easy observation about operators. Suppose we have two operators. One is nilpotent of order 2, and the other one is positive of rank 1. And they commute. Then it's easy to show that they must be orthogonal to each other. It's really easy to prove because take this E, rank 1 positive operator. We can diagonalize it in some basis. It will look like some number, and then zeros. And now if we write x in the same basis, since x commutes with E, it will have block diagonal form, number and then something. But the only number which is nilpotent is 0. So x will look like 0 then something, and E looks like something then 0. So when we multiply them, of course, it will be a 0 product. So it's obvious thing, but we will need an approximate version of that, which says that if we have a rank 1 positive contraction and a nilpotent contraction of order 2, and they almost commute, then they must be almost orthogonal. So again, it's a stability result. And to prove it, one needs to use liftability of nilpotents. More generally, if we have a positive operator, say contraction, of rank n, and a nilpotent contraction of order n plus 1, and they almost commute, then E and x to the n have to be almost orthogonal. We are going to use it now. So now we have a sister algebra which satisfies Phillips condition of order n, which means that A is generated by elements with global rank not larger than n. We want to prove that the central sequence algebra is n subhomogeneous. Again, let's try to show that let's look at nilpotents. Let's try to prove that all nilpotents in the central sequence algebra will have order at most n. So let's, for the sake of contradiction, assume that there is a nilpotent of order n plus 1 in the central sequence algebra. Dividing by its norm, we can assume it's a contraction. Now, the central sequence algebra is a quotient sister algebra by definition. It's quotient of the set of central sequences by sequences converging to 0, and possibly also modulo the annihilator. So it's a quotient by definition, and nilpotent contractions lift. So we can lift our nilpotent contraction to a central sequence. So we have now a central sequence whose each coordinate is a nilpotent contraction of order n plus 1. Now take a positive element in our sister algebra A of global rank n. Then our central sequence approximately commutes with this element just because it's central sequence. And therefore the same holds under every irreducible representation. So let's see what we have here. We have here a nilpotent contraction operator rho of xi, and we have a positive rank n operator rho of e, and they almost commute. So by our lemma, they must be almost orthogonal. And since this holds under every irreducible representation, it's not hard to see that In fact, the same should hold in the original sister algebra. So it means that our sequence xi in the power n approximately annihilates every element of global rank n. But elements of global rank n generate the whole sister algebra. So it means we can replace E by every element, by arbitrary element. So xi in the power n approximately annihilates every element. So it means that xi in the power n is a representative of a zero sequence, of zero element of the central sequence algebra. So we obtain that our original element in the power n equals 0. That's a contradiction because we assume that it's only a nilpotent of order n plus 1. So we got it. If A has Phillips condition of order n, then the central sequence algebra is n subhomogeneous. And the other direction I don't tell you, but it's true. If A is CCR algebra, then f of A is n subhomogeneous, if and only if A satisfies Phillips condition of order n. So for CCR sister algebras, everything is clear. And for type 1, not CCR algebras, it's also clear. In this case, central sequence algebras are not even residually type 1. And for not type 1 algebras, everything is clear by Ando and Kirchberg's result. So we get to final result. The central sequence algebra is n subhomogeneous if and only if A satisfies Phillips condition of order n. In particular, if you take n equals 1, we get an answer to the question of when the central sequence algebra is abelian. It happens if and only if the sister algebra is a Phil algebra. Well, that's it. And thank you very much for your attention.
Thank you, Tanya, for your very interesting talk. Questions, please.
Well, I wonder concerning the functor f. I mean, what will be f of a quotient by with respect to some ideal? Do you have some formula for that?
It's also will be quotient. So,
Okay.
so it passes to quotients. That's Kirchberg proved that.
Okay. And some morphisms or homomorphisms would be vanish, right? If you apply f.
You mean that it might be
For example,
some
from A to
quotient
B, if you
map?
apply an f,
Yeah, of course.
something.
It might happen. Yeah.
And what happens if you apply twice and nothing, right? Or
If we apply twice,
I mean, f of a,
yeah,
it will
it's
be the
yeah.
same.
Some often it will be the same. For instance, if you take a simple purely infinite sister algebra, its central sequence algebra is um no, sorry. But for instance, if you take the algebra of compact operators, not
Yeah.
containing compact operators, but just compact operators, its central sequence algebra is in fact complex numbers. Take again central sequence algebra, it's again sister algebra of complex numbers. So it can stabilize in such a way.
Yes. Yeah. Okay. Okay. Yeah. Thank you.
More questions, please.
Yes, thank you for a very interesting talk. So you have a criterion for f of a being n subhomogeneous. Can you go maybe a step further and can you say anything what happens if f of a is nuclear?
When f of a is nuclear,
Yes.
um, it never happens. No, it's in a unital case. It never happens. So um, um, Elias Farah and Ilan Hirschberg proved that recently that a sister algebra, the central sequence algebra in unital case, is either subhomogeneous or non-exact.
I see.
But what happens in non-unital case is absolutely not clear. Would be really interesting to know whether it, for instance, can be nuclear.
Okay, thank you very much.
More questions, please. Well, if there are no more questions, we thank the speaker again.
And thank
very
you.
much.
Thank you very much.
It was really nice to see you.
So next time we meet in 2 weeks on the 8th of May, because we have a public holiday in Russia on the 1st of May.
In Sweden also.
О,
Okay.
тоже День труда и весны?
Ага.
О.
Ну да,
Ну,
да. Труда только.
Okay.
Ладно, тогда
Ладно.
всем всего доброго, хороших праздников.
Всего доброго, хорошо.
Хорошо потрудиться на 1 мая.
Хорошо.
До свидания.
Спасибо.
Да.
До свидания, дорогие друзья.